Hi everyone, I'm Pallavi. I'm a postdoc in LITS at MIT. I work with Professor Maria Illich, and this work is on unified energy space modeling of multi-energy carrier systems applied to industrial HVAC, where HVAC stands for heating, ventilation, and air conditioning systems. So let's look at what is the motivation behind doing this work. Modern infrastructure reflects energy nexus of multiple sources like gas, electricity, air, water, etc. Different energy systems are modeled by unique tools but suffer from complexity, high computational burden, and low accuracy due to the lack of measured data for modeling. Many of these tools that exist are closed in nature, meaning they can be applicable only for a specific energy systems but cannot be applied to another system altogether. What we need is a unified modeling approach which interfaces different energy carriers under common modeling variables. If we look, energy and power are such common parameters that are attributed with all energy systems like chemical, thermal, electrical, mechanical, etc. A novel approach is presented in this work which specifies the internal physical processes into aggregate variables of energy and power, and the behavior of each component is characterized during the interface variables using the physical energy theorems of the first and the second law of thermodynamics, which are explained here. If we look at the methodology, we see different energy systems like electrical energy systems or mechanical like translational or rotational or fluid energy system or thermal energy systems. We see that every system has its corresponding effort variable and a flow variable. Using these definition of effort and flow variables, we can define the real power in electrical energy system, which is defined as the product of voltage and current, and the reactive power, which was first introduced by our group in this publication, where we say that the reactive power, even for non-sinusoidal, non-periodic signals, can be defined in time domain as VDI minus IdV If we find the analogous effort and flow variables in different energy systems, we would be able to define the real power and the rate of reactive power using the effort and flow variables directly. Now the question is, how do we really incorporate not just the first law of thermodynamics, which can be defined in terms of real power, but also the second law of thermodynamics, which needs the reactive power. This can be done across every single component, which we will show in the following slides. And therefore, we define the real and the reactive powers for every single component, despite of its multi-energy nature. It could be gas, electricity, water, air, thermal, whatever is its nature, we would still be able to characterize it using the real and the reactive power interface variables. So let's look at the complex industrial HVAC system where the heating and ventilation and air conditioning is happening using different energy carriers. For example, this particular example has a big energy station where there are gas-fired chillers, gas-fired boilers, electric chillers, and the storage tanks, which comprise the energy station where the water is cooled. That water is further pumped into the water flow network and it enters the coil, which is a heat exchanger, which also takes air from the airflow network through the fans and from the atmosphere. The heat exchange happens between the water and the air, and the air is cooled and further given to the environmental zone, which is thermally controlled to a certain temperature and humidity. And this interfaces with the outside world using its building shell in terms of the radiation from the sun, etc. And whatever is the water is returned back to the energy station and cooled back again and stored. And this cycle continues. This is the basic big picture how the entire industrial HVAC system works. And here we divide the system in terms of the different sub components like the water flow system, airflow subsystem, energy station, thermal subsystem, etc. And in the next slide, we will see how we can divide, what is our approach to divide these systems into the interface variables of interest. So we see that the proposed energy space models use a unified approach of energy and power interface variables, which is made possible using the analogies of effort and flow variables across different energy systems. For example, electricity as a carrier has electrical energy in it. Gas as an energy carrier has fluid energy in it. Water has both thermal and fluid energy. And similarly, air has both thermal and fluid energy. So how do we characterize our different equipments within the HVAC and say that what is the equipment's energy carrier, what is its energy input, and what are the control variables or the performance matrix of that particular equipment. For example, we start with the simplest system, which is a variable refrigerant volume in the airflow subsystem. It has air as its thermal energy carrier, and it takes electricity as its energy input, and the performance matrix or the control variable here is the output air temperature. Similarly, when we talk about a more advanced equipment called fan coil unit, it takes in the air as well as water from the energy station and exchanges the heat between the two, and that air is pumped into the thermal zone through the fan. Again, here we show that there's another advanced version of a air conditioning unit, which is called as air handling unit. It has the power of taking the air not just from within the system, but also it can draw the air from the atmosphere. So it purifies it, exchanges the heat with the water in the coil, and then pumps the air into the thermal zone. So you can see here very clearly marked what are the measurements available at every port of this different equipments, and what are the energy inputs in the system, what are the control variables, and what are the flow variables like water or air, etc. Similarly, when we see the energy station components, for example, we have the boiler, we have the chiller, we have the gas fired chiller. So the temperature of the water is the control variable in all these three equipment. And the energy input, depending on the type of the equipment, could be gas or electricity. And the energy carrier is water in all the cases, which has both thermal and fluid energy. Moving on to the water flow subsystem, which has pumps and storage tanks, we have seen that the measurements are typically the temperatures, the pressures across the pumps, and the water is the energy carrier, which carries the fluid energy, which is pumped into it, and the energy input is it depends on the equipment. In this case, it is electricity. In this case, it is intrinsic because water itself takes the energy into the tank and that gets delivered to the coils. Conventional models typically use a reduced decoupled model where if you see for an electric chiller, the temperature of the water at the output is the state of the system. And this is a differential equation where you can see as an intrinsic nature. And these parameters need to be computed to be able to model the system eventually. However, in the energy space model, we have linear equations in terms of the energy and the rate of change of energy or the power, which says that at all the interfaces, the real power and the rate of reactive powers are noted. And using these values, P and Q dot, we will be able to find the stored energy within the system and its rate of change. These are the first and the second law of thermodynamics qualitatively. So let's look at the available measurements that are typically available in an industrial chiller, electric chiller. So you would have the current, which is going in and out, the mass flow rate of the water, the pressure at the input and the output of the water, the temperatures at the input and the output of the water. So the power using this particular flow diagram, if you remembered, what is the power input into the system, what is the power output, and using the Telegins theorem, we can see the net power within the system is the sum of these powers, and the power that is going out, we subtract that power. So if you see here, what we have done is we calculate the powers using the analogous voltage and current parameters, and remember not just the thermal energy, we also have the fluid energy within the system, and using the Telegins theorem, we wrote the net power in the electric chiller. Similarly, we wrote the rate of reactive power within the chiller. And you see, this is so simple that directly using the analogies, we were able to find what are the interface variables characterizing the behavior of the system when it interacts with different systems in its surroundings without really looking into the states of the system physically. right? Without in-depth model parameter extraction of the physical processes, we were still able to characterize the system just using the terminal measurements, which are limitedly available. So if we look at the pump, again, using the same analogies in different energy systems, we were able to find the real power and the rate of reactive power across the pump. So you can see the energy is coming from the water, from the coil, from the electricity that it draws energy, and it gives some energy out to the chiller in terms of the water. So that is subtracted. Similarly, the rate of reactive power is noted, and all these variables like powers are computed using the available measurements at the terminals like the voltage, current, pressure, mass flow rate, etc. Similarly, for the coil, it is a little more complex because we have four ports in this case, as the water is pumped in and pumped out, and the air is pumped in using the fan, and it is drawn into the thermal zone. So there's a heat exchange which happens between the air and water within the coil. And similarly, we can write using the analogies, the real power terms and the rate of reactive power terms. And using Teligand's theorem, we can again find the net real power and the net rate of reactive power in the coil. Now, if we see that once we have these basic blocks characterized using the real and the reactive power interface variables, we can decompose all the complex systems of the multi-energy equipment into these basic building blocks. For example, the fan and pump are analogous. They have energy space model with air or water as the respective energy carriers. Otherwise, the equations remain the same. Only the carrier changes, air or water. Similarly, the fan coil unit basically is built with fan and coil superimposed. So both the models need to be combined to get the FCU model. AHU is actually very similar to FCU if you see the block diagram here. The only difference is that it has the provision of drawing the excess air from the atmosphere. So uh, mass flow rate of the air input and the output are not same. So that is important to note. Similarly, if you look at the boiler and the chiller, the only difference between them is either gas or electric input, and the temperature of the output. Water would be hot here compared to this case, which would be lower than the input. Similarly, the gas chiller has the difference between itself and the electric chiller in terms of the energy input. Here it is electricity, here it is gas. So similarly, cooling tower is also very similar to the chiller without the electricity input. So, once we have one model made, for example, for the chiller or the pump, we can actually characterize the entire industrial HVAC using these basic building blocks because the systems are very analogous and linear in the energy space with power and the reactive power. So, in conclusion, we have been able to develop a unified modeling theory for multi energy systems using the energy and the rate of change of energy, which is the power. And this proposed model is not just for having a unified model, but it further leads to design a physically implementable optimal control of the system, which saves energy, cost, and carbon. It finds direct application in characterizing components which have limited information in terms of measurements or equipment specifications from the manufacturers, which is typically the case in industrial equipments. You are not allowed to really get into the system and take the measurements out. These are closed systems typically. But just with the limited measurements, we've been able to model the system, yeah, as you can see. And this optimizes the physical efficiency in energy conversion processes because it takes care of both the first and the second law of thermodynamics, where the rate of reactive power is actually studied. And We can see that the aggregation of variables makes things very simple, and we are not just talking about one or two variables across different energies like thermal, electrical, mechanical, chemical. We were able to find energy and power and combine them together without really going into the physical working complex of the complex systems. Just looking at the interface, real power, reactive power, we were able to characterize the system and model the energies of the system. So these are some of our references. And if you have any questions, please feel free to reach out to me or my senior author. Thank you so much for listening to us.